Hello students, welcome to this particular lecture on Elmore delay. So in this particular lecture, we will look into one particular uh, model of delay that is called as an Elmore delay model. We will arrive at the estimating the delay of second order circuits using an Elmore delay. So we'll be deriving the expressions that has been used for the Elmore delay method, right? And one of the reasons for having this particular Elmore delay method is to make use of this model for a higher order RC circuits. And these RC circuits are nothing but the model switching resistance and then the parasitic capacitances that has been modeled from the transistor based circuits. So if I'm looking at a very higher order digital circuits, looking at the higher order digital circuits, we will then approximate into an higher order equivalent switching resistance and then the capacitance model. And applying the Elmore delay method on this higher order RC circuit should be able to give us the propagation delay falling or rising, or even the contamination delay falling or rising. So to obtain those values, we use this particular Elmore delay method. It turns out that the Elmore delay method is kind of a nonlinear model, but it is very very effective and it is very very handy to use, or rather it could be very easy to use as well. Um, so let's draw a three input or a two input NAND gate. So let me draw a very simple one, a two input NAND gate. So I'm going to draw on the PMOS side. So this is a PMOS, a two input NAND gate connected to the VDD source, and this is a PMOS transistor, and then this is my uh, uh, this is my, let's say, yeah, I think it should be a NOR gate. So two input NOR gate, sorry. So that is output, and here I have on the uh, yeah, on the pull down circuit I have the NMOS transistors. So this is my A and B, and then this is my subsequent A and B on the pull up side. So yeah, so this is a two input NOR gate. Let's say that I have the switching resistance also estimated for each of this transistor, assuming that the widths and then the lengths of the transistors are the same on the PMOS and then NMOS side. So let's say that I have this as nothing but an equivalent resistance of R. This is nothing but an equivalent resistance of R. And if I want to find out, um, what do you say, the propagation delay of the rising. So if I want to find out the propagation delay rising for the circuit, I need to have the capacitance. I know at the output node. At the output node, I will have some kind of an equivalent capacitance. So I'm just going to write it as C load for time being. We will be able to estimate it, the exact value of the capacitance at the output node once we learn the diffusion capacitances. And then we will also have some kind of a capacitances here. So I'm going to draw that some kind of a capacitances at this particular node. So I'm going to write it as C diffusions. So what we have is a source node here, VDD, right? And then a resistance, switching resistance of the transistor A, the PMOS transistor A, and then connected to the C diffusion capacitance. And then we will have one more switching resistance of the transistor B, and then we will have the load capacitance, C load capacitance or the C output capacitance, right? So it is basically a two order circuit. So if I want to draw it in terms of an RC circuit, it will be in this form, VDD, and then I have the R of the A PMOS transistor, and then I'll have the capacitance here. I'm going to write it as C diffusion, and then I'm going to have this R of the PMOS transistor on the B side, and then we will have the C load capacitance or the C output capacitance. All right, so this is my output node Y, and then this is my the source power supply VDD. So in this case, if I want to find out the propagation delay rising, right, PBDR rising, right, for the output node Y, it becomes a 2 or second order RC circuit, right? So it's an RC circuit, but it is a cascaded RC circuit or a second order RC circuit. All right. And so if I have a three input, if I have a three input NOR gate, I will in fact have for the calculating the propagation delay rising, I will have a third order RC circuit. So one more RC network will get cascaded. So I will have RA, C diffusion, RB along with the C diffusion, and then RC along with the C load or the output capacitance. So on. So if I want to find out the N input NOR gate rising delay, I will have n such ordered RC circuits. In the other way, on the pull down side, if I want to find out the propagation delay falling for a 2-input NAND gate, again instead of the VDD, we will have the sourcing node or the sinking node will be the ground. So instead of this VDD, we will have the ground, and then the capacitances will be discharging. So the C load will be discharging through the two of the transistors A and B, because on a 2-input NAND gate, we will have on the pull down side, the transistors A and B will be in series, and on the pull up side, we will have the A and B transistors to be in parallel. So in a digital circuits, if I want to find out an equivalent the propagation delay falling or rising for a higher order digital circuits, then we need some method which will be able to simplify our higher order RC circuits, because RC circuit is actually coming from simplifying or approximating our transistors into an switching resistance and then the capacitance. So anyways, we are going to do that. So ultimately we will have, for a higher order digital circuits, we will have a much higher order RC circuits, and we need to find out a method which will help us in establishing the delay for this higher order RC circuits. And Elmore delay is one such method. Okay, moving ahead. So I've taken a very simple second order RC circuit. So I have R1 and C1. So R1 here and then C1 again cascaded to R2 and C2. And we need to find out the delay of the RC circuit. All right. So I have two nodes. One is the output node here, V out. Another one at this point of time, I'm going to call it as V1. Right. So there are two nodes, V1 and V out. I know this current I1, which is flowing across this capacitance C1, will be nothing but C1 dV1 by dt. So this is my charging current. Again, we can consider this R1, C1, R2, C2 as nothing but an approximated RC equivalent circuit coming from the 2-input NOR gate, right? And I have this current I1, and I will have my current I2, which is flowing along this branch of C2, can be considered as C2 into dV out by dt. So this is again a charging capacitor charging current equation. Now I will be what we really want is to find out an expression for V out at this point of time, and similarly, once we will be able to identify the V out expression, we should be able to find out what is the expression for V1, right? So what we had seen in an inverter circuit, V out, initially it was a linear and then exponential, and similarly, V1, or rather, the output of the inverter circuit, we had a linear and an exponential model, and then from there we were able to find out what is the propagation delay falling. And for an inverter also, what we did was we calculated, we identified the switching resistance and then the capacitance. And now we are stating that whatever is the load capacitance seen at the output node multiplied by the switching resistance will be my propagation delay. Right. So assuming this R2 and R1 are my switching resistances. So these are nothing but the switching resistances coming from the transistors. Right. Switching resistances. So here also this is nothing but the switching resistance. R1 and R2, right? C1 and C2 are coming from the whatever is the capacitances seen at the node V1 and seen at the node V out, right? So C2 can also be considered as the parasitic capacitances or the depletion capacitances or the diffusion capacitances of those particular transistors, as well as the wire capacitances, as well as the input capacitances coming from the next stage. So if there are two stages, one stage cascaded to another stage. So the output node, we will have an equivalent, or the sum of all the capacitances will be nothing but the diffusion depletion capacitance plus the wire capacitances plus the input capacitances, right, coming from the second stage. So that's about the C1 and C2. Right, so what I'm going to do is, we want to find out the solutions of Vout and V1. So in that case, we'll try to apply some KVL method. So one KVL we will apply it in this particular branch, and another KVL we will apply it in this particular branch. Right, so this the first KVL is this one, VDD minus of, so the current that will be flowing across this R1, which is nothing but I2 plus I1. So at this particular node, there are two currents getting distributed, I1 and I2. So across R1, I think there will be a cumulative currents of I1 plus I2. So that's what I've written here, I1 plus I2 into R, minus of this node voltage of V1 is equal to 0. So VDD minus of R1 into this I1 and I2 is coming from this capacitor charging current equation, C1 dV1 by dt, and C2 dV out by dt is this one, minus of V1 is equal to 0. So I have this one particular equation coming from the KVL loop of 1. On the second one, on the second KVL loop here, we will get V1 minus of I2 R2 minus of V out is equal to 0. So that's what I've written here. And we will get V1 minus R2 C2 dV out by dt. So this is dt here. So let me try to, dV out by dt minus of V out is equal to 0. So that's what we get here. So this is my first equation, and then this is my second equation coming from the KVL loop. All right. So let me minimize this so that I will have perfectly ordered, maybe a little bit more. Yeah, and I think this is perfect. Yeah, moving ahead, I have two KVL equations. So if I put, okay, let's go back. What we want is basically, we want a solution of V out at this point of time. So, if I can somehow have this, either of one or two equations only in terms of V out. Right, it could be differential, first order differential of V out, it could be V out, it could be second order differential of V out also, but there should not be any V1 terms among this one and two equations. So what we are going to do is substitute 2 in 1. So put this in here, and we want to erase out V1. So I will substitute V1 is equal to nothing but V out plus R2C2 to dV out by dt, and then put it in this particular wherever the V1 terms exist. So put it there in terms of V out, so that I will have all the equation of the first equation, the first KVL loop derived equation, everything in terms of the V out. Right, so that's what I've done here. Put 2 in 1 gives VD minus R1C1 dV out by dt plus R2C2 dV out square by dt square minus of R1C2 dV out by dt is equal to this one. So if I look closely into this, I will have a constant value, and I have this dV out by dt. I have this dV out by dt, the first order differential of V out. I have this dV out by dt. Okay. So if I take this dV out by dt on the left hand side common, so I will get R1C1 plus R1C2 plus R2C2. R2C2 will go here, will become minus. So if I'm taking this minus outside, everything will become plus. So R1C1 plus R1C2 plus R2C2, right? And then I have this second order differential term, right, which is having a constant of R2C2 and R1C1. So that's what I have written here. VD is equal to V out plus everything. So this particular term, we are going to neglect it, saying that this second order differential, with respect to time, is going to give me a very, very small magnitude value, very, very small magnitude value, and that is something we are going to ignore. And this assumption, and so we are going to ignore this, and this assumption we are making it because, as we have seen from the inverter output voltage profile, it is going to be linear profile, and then it is going to be gradually going towards the exponential profile. So if I consider a linear profile, decreasing linear profile or increasing linear profile in this particular case for the charging, for the rising time, So the increasing linear profile, if I do a first order differentiation, it will be a constant, and if I do one more time of a differentiation, it will be a zero, right? So if it is a linear profile, or if it is an exponential profile going towards an exponential profile, so we are assuming that it will be somewhere there, and thereby its second order differentiation will be very small. So we are going to ignore that. So ignoring that, what we get is the first order differential, V out term, and then VDD. So what we are having is a VDD minus V out minus of A into dV out by dt, where A is nothing but R1 C1 plus R1 plus R2 into C2. Okay, so let me go back a bit just to identify this particular expression, which is kind of very important. So I have R1 C1, and then this C2, if I get it common, I will make R1 plus R2 in brackets, right? Very important at this point of time. So moving ahead, so I have this particular equation, and then this particular equation we have anyway seen in the capacitor charging profile. So if I take VDD minus V out is equal to A into dV out by dt, and then dV out by VDD minus V out will be equal to dt by A. Taking the integration on both the sides, starting from 0 to V out of t, and then 0 to t at particular time t. At this particular time t, we are interested in finding out what is the V out of t, right? And then if I solve this particular integral, I will get the solution of this particular integral on the left hand side will be nothing but the log solution, and the limits will be 0 to V out of t, and is equal to, on the right hand side we will get t by a, and the limits are 0 and t, so that's why I will get the solution of t by a. So further resolving this log of VDD minus V out of t divided by VDD is equal to minus of t by a. So eventually I should be able to find out what is V out of t. So V out of t is nothing but our capacitor charging current equation, charging voltage profile equations. So it is nothing but V out is equal to 1 minus e raised to minus t by a, and then multiplied by VDD. So very similar to our capacitor charging, right? Where A is, if I consider this A value, that is coming from that constant R1 C1 plus R1 plus R2 into C2. Right, so this is what the profile I've drawn here. So the V out profile, so I should have written V out of t with respect to t, and at 63% it is the tau, which will be nothing but my A. Again, this is the second order d2 V out by dt square is something we have ignored, and then we got this approximated capacitor charging profile, which turns out to be very close to our if I consider the R1 C1 and R2 C2 and put some values in R1 and C1 and R2 and C2 and find out the output voltage, this comes out to be, even if I consider the second order differential, if the SPICE considers that, and then if I find out the V output with respect to time, either in a multisim or in an LT SPICE, I'll get close to this particular voltage profile. Right, so ignoring D2, ignoring the second order output voltage is giving us a very close value, although not accurate value, but it is a very approximate value. So in that sense, we are good. So this is what we get, right? And if I look into the input side and then given to a circuit and then taking the output. What we have analyzed is for an inverter circuit, it will be R into C, right? And that will give me the propagation delay to be very conservative, assuming that the input side is not a step input, it will be some kind of a ramp input. Then at a conservative approach, we are saying that at the output side, the propagation delay falling or rising will be equal to that of R into C. So that is what we will come to. So this time constant, also it looks like a time constant. So this becomes our, the delay parameters. This becomes the delay parameters. Assuming that the input to the 2-input NOR gate is not a step input, it will be a ramp. Then this becomes my rising delay, the propagation delay rising for the 2-input NOR gate. Right, now what we are interested in is there were two nodes, V1 and V out. We are also interested in finding out the V1. Okay, And I have two KVL equations written down. So what we want is basically from those two KVL equations, we want all the terms in V1, whether it could be, dV1 by dt, that's also fine. V1 in terms, V1 and then constant, that is also fine. But what we don't want is anything, V out term. So if I go back to this particular, the starting equations, so I have these two equations. So what we want is, everything in terms of V1, because we have anyways calculated the solution for V out. So similarly, we want to derive an expression for V1. So I have in this, in the first equation, I have this V1, I have this, this particular term to be dV1 by dt, and then this is anyways a constant value. So I need to replace this V out term. Second equation gives me V out in terms of dV out by dt and then V1. All right, so if I put this 2 in 1 here, all right, so I will get this V out, so differential of this V out. So I have to do a differential of this particular terms. Right, so I will get a second order differential of V out by dt square, and then I will anyways get a single order differential of V1, which is fine. And then second order differential of V out, anyways, we are going to ignore it. Right, that's the same thing which we have done in the last solution while we were trying to find the solution of V out. So similarly, for finding the solution of V1, we are going to ignore the second order differential of V out. Moving ahead, so we were somewhere here finding the V1. So put this is basically the second equation, putting it into a 1 and then ignoring the second order differential of V out with respect to dt square. So this is what we are ignoring. So finally we will get VDD, this is what we get, minus of V1. So this particular term is kind of very, very interesting. So finally we have VDD minus B, where B is nothing but R1C1 plus R1C2, minus of V1 is equal to 0. So everything is in terms of V1, and this VDD is anyways a constant. So V1 of t will be nothing but VDD into 1 minus e raised to minus t by B, where B is my time constant and it's also R1C1 plus R1C2. Right, again, I mean, how do we arrive into this from this particular expression to this particular solution is, integrating on the both sides and then putting the limits of 0 to V1 and then 0 to t on the time side as well as on the voltage side. We should be able to get this particular expression. Very, very similar to what we had derived for the V out expression. Right. So the propagation delay rising, right, from the source VDD to the V output node is nothing but R1C1 plus C2 into R1 plus R2, and the propagation delay rising from the source VDD to V1 is actually nothing but R1C1 plus R1C2. Right, I'm actually ignoring a log of 2 here. Log of 2, you can take it with the consideration that the input will be a step input, but if the input is not a step input, then we will take the conservative approach and have only the sum of this products of R and C. All right. So this is what we get, the propagation delay rising for for the V output node and then the V1 node. Right. Looking closely at it, I have one term R1C1 and R1 plus R2 into C2. Right, so I have this term, there is one R2 into C2 is extra as compared to that of for the propagation delay rising for the V1 output node. Right, so if I compare actually these two equations, what we get is the delay for the output V output node to reach to the 50% or the halfway point of that VDD is actually more. So this is R2 C2 more. All right. Hope you have understood this or you have analyzed that. So coming back to our original circuit of VDD and then R1 and C1, and then I have this C1 here, and then I have this R2, and then I have this C2. What it says is the propagation delay, in this case it is rising, right, is nothing but the summation of R into all the node capacitance is also called as the leaf capacitances, right? So the capacitances connected to the individual nodes. So I'm going to write it as 1 and then 2, right? So it is nothing but the propagation delay rising or falling. In this case, it is rising because the VDD is connected. So it will anyway is going to charge the capacitance C1 and C2. So the rising propagation delay will be nothing but some R multiplied by this capacitance C1 and then some R multiplied by this capacitance C2, right? It includes all the leaf capacitances. It includes all the node capacitances, right? Now this particular some capacitance R here, some in the sense some value of capacitances, right, is it depends on, right, the node I'm selecting. Right, let's say that I'm selecting a node 1 here. So this is my, so we are interested in finding the propagation delay of the node 1. So the node 1 achieves the 50% or the halfway point of the VDD, so what is that particular duration once it reaches the halfway point of the VDD? So in that case, so this is my node of interest. Right, so my propagation delay rising turns out to be, from my previous calculation, from my previous second order RNC network calculation, it turns out to be R1 C1 and R1 into C2. It's very, very interesting that it doesn't accommodate R2 at all. Right, although we know that in charging this capacitance, in charging this particular capacitance C2, it takes R1 and R2 path. All right, but for approximating, because we have ignored that second order dv out by dt square, dv out d2, this particular ignoring d2 v out by dt square, because of this ignoring this particular term, we have actually made the second order RC circuit equivalent to a single order RC circuit, and then estimated the time constant, which is nothing but the propagation delay rising, right? So just for our simplified calculation, right, it doesn't account R2, right, while finding the propagation delay for the output node 1. If my node of interest is 1, it doesn't accommodate R2. All right. Now this R1 and R1 here, if I consider the capacitances C1 and C2, right, it is also called as the shared resistance for the capacitance C1, and of course the shared resistance for the capacitance C2. Okay, that's how the nomenclature has come. Now what is this shared capacitance? Right, what is this particular shared capacitance? Right, the shared capacitance is nothing but a common capacitances between the two paths. And what are these two paths? One path is the path from the source, right, the path from the source to that of the node of interest. So this is my path, and here whatever the resistance I see, I'm going to write it down as R1. That is one particular part. The other path is isolated, or the other path is very discretized for the capacitance, individual capacitances. So if I'm actually finding out the shared resistance for the C1 capacitances, right, then my other path is nothing but the path from the source to that particular capacitance node. So the resistive path I need to find out for C1 will be nothing but R1, right? So I'll use a different color. So this is my one path. That path is common for both the capacitances C1 and C2. If I want to find out the equivalent or the shared resistance for the C1 and the shared resistance for the C2, that particular path from the source to that particular node of interest, that becomes same. So this is my first path, the resistive path. The second resistive path is with respect to its individual node capacitance. So for the C1, I will have the path of R1. For the C2, I will have the path of R1 plus R2. All right. So in that sense, if I want to find out for the C1 capacitance, right, for the C1 capacitances between the two paths 1 and 2. So this is my second path, right? So this is, I'm going to write it here. So for the C1 capacitances, there are two paths. One is coming from the source to that node of interest, which is R1. So I'm going to take it R1. And then the second path is nothing but from the source to the leaf capacitance or the node capacitance C1, which is R1. So the common here is, or the shared one is nothing but, the output of this is nothing but R1. So that's what I'm going to write. So this is my R1, which is nothing but the shared resistance for the capacitance C1. For the C2 here, first path, resistive path is R1. The second path is actually from source to the C2 capacitance is nothing but R1 plus R2. So the common here is nothing but R1. So I'm going to take it as R1 here. So that becomes my shared resistance for the capacitance C2. Right? So my propagation delay rising for, if my node of interest is 1, is nothing but the shared capacitances, which is nothing but R1 C1 plus the shared resistance into C2, which is nothing but R1 into C2. All right. And if I similarly do it for the second node of interest, the first path for the second node of interest will be nothing but R1 plus R2. For C1, the resistive path will be R1. So in that case, my common resistance will be R1 for C1 capacitance, right? For the C2, my resistive path is nothing but R1 plus R2 because this is my node of interest. And the resistance path for the C2 is nothing but R1 plus R2, right? So my the shared resistance will be R1 plus R2. Right. So the propagation delay rising is considered as R1 C1 plus R1 plus R2 into C2 if I'm considering the V output node, right? And then if I'm considering the V1 node, it is nothing but R1 C1 plus R1 into C2. I'm ignoring this log of 2, that is nothing but 0.693. Assuming that the input side, it is not a step input, it could be a ramp input, it could have some kind of an input transition. So the Elmore delay method is nothing but this particular expression. So the TPD of, it could be a propagation delay falling or rising, is nothing but the summation of considering all the capacitances in the circuit, right, multiplied by the individual shared capacitances. So all the capacitances at the node I multiplied by the shared resistances for the node I. Right, and it could have n nodes, so it will be from 1 to n nodes. It should include all the capacitances in that particular circuit, right, and then multiply by that with that of the shared resistance seen by the individual node capacitances. Right, hope this is clear. Just for a better understanding, I've just written it here. RIS is nothing but the shared resistance from the node, the node from which the capacitance is connected to all the sources, whether it is VDD or ground, for VDD for rising, ground for falling output, and whatever node is my output node of interest. So the output node to that particular source power supply, right? Whether it is a VDD for rising and then 0 for the ground, right? So in the same way, what I had shared in the 9th slide, the shared resistance from R, for the node C1, V1 of interest will be nothing but R1 here for the capacitance C1, and then R1 because it is common for the capacitance C2, right? And then we get this propagation delay rising for the V1 node of interest.